So welcome to my little talk about device tracking via Linux new TCP source port selection algorithm. Maybe some of you still remember the Meltdown and Spectre attacks that caused quite some concern in 2018. And these attacks exploited performance features of modern CPUs and were thus able to access data that shouldn't be accessible. And these two attacks also demonstrated a broader principle, namely that complex systems often leak information that shouldn't be accessible by side effects. And in a similar spirit, these three guys here found an attack that exploits Linux TCP source port selection algorithm, and it uses the side effects of hash collisions to track devices across networks and browser sessions. And this attack is a browser-based device tracking technique, and it uses information collected through the web browser, and it's of course a privacy risk because people are often unaware of this tracking. And often in this device tracking scene, there is the so-called golden image challenge. It's the challenge to distinguish identical devices across networks and so on, but that have the same hardware and software configuration. And this attack by these three guys is actually able to pass this golden image challenge because it has a device-specific key that gets generated at startup. It persists browser sessions and network changes because it's on the kernel level at startup. And this technique is a so-called fingerprinting technique. There are two types of techniques, tagging and fingerprinting, and this is a fingerprinting technique that measures characteristics of a client device and generates a fingerprint. And I think tagging is not our concern today. And then we come to source port selection. Basically, if you are around on the internet, you are always communicating with the so-called four tuples out of IP and IPs and ports, for source and destination. Basically, you can see as an analogy maybe that you want to identify where someone lives, and then you don't not only need to identify a connection between the two buildings and where you live. You would, for example, not only need the street number, but also the apartment number to identify where exactly someone lives. And and source port selection has the task to complete a 3-tuple into a 4-tuple by calculating the source port. And the source port selection basically has two goals. The first goal is functionality, because reusing source ports can cause failures because TCP is asynchronous, and because of this, you might have already sent your last package, but there are still packages arriving, and you're still in a so-called time wait state. And this can cause failures. That's why you should omit reusing source ports too soon. And then a second goal is security, because there are off-path attacks, and it's also possible to determine your device activity. And off-path attacks are, for example, if your source port is too easy to guess, then an attacker must only guess the TCP sequence number and might be able to hijack your TCP connection. For example, because and what I wanted to say, and it's called off-path attacks because it's not on the path where the bit of the client and the, for example, tracking server, but it's or the server, but it's on because the attacker can be at some completely different location, and it could still interfere into your TCP connection, because if the source port is too easy to guess, he just has to guess the sequence number and has a higher chance of hijacking your TCP connection. And device activity can, for example, be that if you have, for example, have one globally shared increment between all TCP connections, then if a attacker, for example, makes TCP connections to a server all the time, and he sees the source port increments and by how much they change, and from this he can deduce the device activity. And yeah, and now we come to the algorithm that gets exploited by the attack developed by the three guys. First of all, we need to know that these source ports are usually divided into ranges. For this attack, we only have to know the ephemeral port range. That are ports that are dynamically allocated by the OS and are short-lived over here. And oops, what did I do? And yeah, and this attack and this algorithm that gets exploited uses two hash functions, fk1 and fk2. fk1 maps to integers, and fk2 maps to the possible indices of a perturbation table. Now you might ask, what is a perturbation table? A perturbation table is basically a table with values, and it has the task to make this incrementation of port numbers separate the incrementation of port numbers into different spaces. And this has the advantage that the port reuse frequency is lower, as stated in the paper, and it's harder to analyze device level activity because you only see, like, if you have one TCP connection, then you only see like one perturbation cell, and you can't guess all the other perturbation cells. And maybe just by coincidence, your perturbation cell is the one that gets all the traffic or no traffic. And yeah, and here's the algorithm itself, the pseudocode. So first, what we do is we calculate the offset with the first hash function, then we calculate the index with the second hash function, and then we use this index to look up in the perturbation table. And so the first one gives us an offset that might be, for example, 50,000, and then then we add up to it the table in the entry of the value of the table cell at this index. And in this case, we are unlucky, and this perturbation cell is already occupied or in use, I mean. So the check for it is over here. And before we made this check, we made an increment to this table value here, and that's why we also we go to the next cell. And luckily, this cell is not in use yet, and we can use it. And yes, and this double hash port selection algorithm terminates if it finds a port, or if it terminates if an error, if it can't find any port to assign when going through all the different ports, and it kind of decrements it every round. And now we come to the actual attack. So the attack basically has two parties. There's a tracking server here and the client device. And first, the client device requests a website. The tracking server sends the website, but it also sends a tracking snippet. It's basically also part of the website. And this JavaScript tracking snippet gets executed, and then this tracking snippet makes several connection attempts with so-called loopback 4-tuples. I explain later what that is, and attacker 4-tuples. And this attacker 4-tuples, this connection attempts go to the tracking server, and this tracking server then analyzes the patterns of the source ports, and is by this so he extracts the source ports from the TCP SYN package, and yeah, it analyzes the source ports and is thus able to derive a device ID, what I am going to explain in more detail in a second. I don't know what I'm doing wrong. Yeah, and as I said, there are attacker 3-tuples. They go to the tracking server, and there are loopback 3-tuples that go to the stay within the client device, and they use so-called loopback addresses that are these addresses with 127. And yes. And the device ID I was talking about earlier is basically a structure formed by collisions of this loopback 3-tuples. And so it's the structure that's built by loopback 3-tuples colliding via this hash function tk2 in a certain perturbation cell. And the interesting thing about these collisions is that they depend solely on the key K2, and they are randomly generated at startup. And this key K2 persists because it's at the kernel level. It persists across browser sessions and network changes. And because the device ID over here depends on the KK2, this device ID also persists across browser sessions and network changes. And yeah, and the device ID actually is so to be precise, the device ID is the pair of so-called pair of independent pairs of loopback 3-tuple collisions and the number of iterations. We will later see why. And every one of these collisions, so that this one and this one collide, is basically evidence of how this K2 maps into perturbation table cells. And now you might ask, what is this? What does independent pairs mean? And independent pairs means that if you, for example, if we have this, if we have this 3 loopback 3-tuples that collide in the same perturbation table cell, then they are basically the binomial coefficient 3/2 different possible pairs that you can make up, which are if you ignore the ordering, but basically only 3 minus 1 are really independent. That's the case because if you, for example, have here 2 collides with 3 and 5 collides with 3, then you don't need to know that that 2 collides with 5, because that's already implied by transitivity. Okay. And now you might ask, why do we need this? Why do we use loopback 3-tuples and not attacker 3-tuples? That's the case because attacker 3-tuples are not consistent across networks, but loopback 3-tuples. So for, maybe an example, if you, for example, I don't know if you know that, but if you, for example, have a Wi-Fi dongle and a normal Wi-Fi card and an Ethernet connection, then often you get a completely different IP address for each of these connections, IP source address. And that means that this attacker 3-tuples are not consistent across networks, and loopback 3-tuples don't have this problem because they always just stay within the device. And for this reason, loopback 3-tuples are used for generating the device ID. And now we come to the so-called sandwiching method technique. And the problem is we cannot directly observe collisions of loopback-free tuples. We can't observe that these two collide with each other because we don't have kernel level access to the kernel level internals. We can't see that they collide actually. But what we can do is we can exploit side effects of this hash collisions, namely this predictable increments. If you remember this line from the double hash port selection algorithm, there was just a really predictable increment by one of every table cell. And thus, what we can do, we can send packages to the tracking server, TCP SYN packages, and from this TCP SYN package, we can extract source ports, and we analyze the source port increments via the sandwiching technique, and are thus able to derive a device ID. And here I want to give you a small intuition into and here I want to give you a small intuition in the general principle of the sandwiching technique. So first, you start with having and maybe a little question: can someone see the sandwich in this image? Does someone want to call it out where the sandwich is? Yeah, I guess I shouldn't ask obvious questions. Yeah, the sandwich is here. We have a wrapper, we have a filling, and yeah, the two wrapper steps and a filling. Yeah, if you use wholemeal bread, it's I guess much more healthier. And in the wrapper steps, you have you use the same attacker. In the wrapper step, you use the same free tuple, but in the filling, you use another free tuple. And that's an important thing to keep in mind. And now we just calculate the double hash port selection algorithm as usual. Then we have this table cell increment. And what we notice is that if we look at this table I, at the table at the index I, then we see that, then we see that in between, until this point, if we say I is equal to j, then we have here a source port increment, a perturbation table cell increment, and here perturbation table cell increment at index I. Because we can basically say here I, and that means that and this means that yeah, we have a increment of 2 compared to the value over to the yeah, anyways, yeah, basically I have an increment of 2 if I and j are equal, and that means that yeah, we had an increment of the perturbation table cell at index I over here. And what that also means is that we have a collision between 3 tuples x and y. If we have a collision of between 3 tuples x and y, what basically means we have that this hash function gk3 maps this tuples x and y to the same perturbation cell, and we have this collision if the port 3 over here at the bottom is larger than port the first port plus 1 over here. And why is this the case? Because if we have something larger than 1, then that means we don't have this case, but we have this case, and that means I and j were equal, and that means we had a collision in the same perturbation table cell. And by this we have a collision between these two free tuples. And so that was basically just a general principle, but in practice we have to also consider some other effects also, because we also have to consider some other aspects, because we also have, I mean, this is a client device. It's also just using the internet as normal, and by this there's also noise by other TCP connection that it makes. And this TCP connection also influences the perturbation table and increment it. That's something we have to consider. And additionally, we have to consider that in my simple example here, I only used a free tuple per step, per layer here. But in practice, that's of course very slow, and we can also send several free tuples in the different layers here and the different steps. We can here send 3 at once and so on. And why does this actually work? This works because from the TCP SYN packages, that's of course simplified here, we can directly extract a mapping from free tuple to source port. And by this free tuple, we can identify which free tuple got which source port. And then we can compare this same free tuple over time and see its source port increments over here. And we also have some limitations to the client device, because the client device, this JavaScript tracking snippet is executed in the browser sandbox. The browser sandbox operates at a higher level than this whole TCP layer operating system structure. And because of this, it has no access to the TCP stack. And for this reason, it has no access to the source ports. And for this reason, we actually have to use the tracking server to get this connection, because it is able to extract this source ports and and it's able to extract the source ports and also this mapping of free tuple to source port. And it uses a nice little trick, that is, it's here's a loopback free tuple, here's a loopback free tuple, and by knowing that these two loopback free tuples collide with the same attacker free tuple, that's this one here, we can, by transitivity, deduce that these two loopback free tuples also collide in the same perturbation table cell. Oh no. And now we start with phase 1. I mean, the next question would be, is there phase 2? And another question might be, why do we need a phase 1? And we need a phase 1 because of this little trick that I showed you on the slide before. We can only deduce that two loopback free tuples collide with each other if we have a attacker free tuple with which they collide. And if, for example, here we have two loopback free tuples, but no attacker free tuple, we can't know if they collide. We always need an attacker free tuple, and for this reason, we need a phase 1 that enables us to collect unique attacker free tuples that collectively cover all perturbation table cells. And a unique attacker free tuple is one that uniquely maps to a certain perturbation table cell. And here's the pseudocode of the phase 1. We start with getting new candidate attacker free tuples, and then we basically have our sandwiching method. In the wrapper we have candidate attacker free tuples, and in the filling we have unique attacker free tuple. The unique attacker free tuples found so far. At the beginning, of course, the set of unique attacker free tuples is empty. And and then the question is, we have a condition down here, if you see my mouse pointer, and this condition determines if a certain candidate attacker free tuple is actually unique. And and now I want to deduce the condition to determine that. And the condition, I made here a little example. And we know, if we know that the source port increment was only 1, like over here, then this means if we follow the paths over here we add the fk2 hash and follow up here. And we see here was no collision in the filling step here. There was only a collision here because it has to be, because it's the same attacker free. It's the same attacker free tuple down here and here, and they cause increments. But in the filling there was no collision. And what does it mean if there was no collision? We know that in the filling there are the unique attacker free tuples, and if there was no collision, that means this candidate attacker free tuple here, this one, is actually the first one to collide with this perturbation. It's the first one to collide with this perturbation table cell, because because here in this set are all unique attacker free tuples that we found so far, and if it doesn't collide with any of these, then it must be unique also. Yeah, and basically we then determine this nice little condition here, if I'm able to switch the slide. And yeah, and this algorithm terminates as soon as the set of unique attacker free tuples is equal to the size of the perturbation table, which is actually our goal, yeah, to have a attacker free tuple for each for each perturbation table cell. But there's also a little problem. We of course have noise in our the client device could make other connections to google.com or something. And for this reason, there could be noise. And this noise is actually able, as you see here was a 1 before, is actually able to hide attacker free tuples, unique attacker free tuple. This would actually be an attacker free tuple if it wasn't for the noise over here at the bottom. Here at the middle, I mean. So, but the good news is noise can hide a unique attacker free tuple, but it can't fabricate one. And over time, I mean, as you know, this TCP source port selection has the goal to not take the same TCP source port all the time. So by some time it will be free again, and this this source port can get a unique attacker free tuple assigned. Now here's the pseudo. Now we go to phase 2. And this is where the interesting stuff happens. No preparation anymore. So here first we increase the iteration counter, and here we also have our sandwich again. And how does our sandwich look like this time? This time our sandwich has the unique attacker free tuples we determined in phase 1 in the 2 wrappers, and a single loopback free tuple in the filling. And how do we now determine if so in phase 2 we basically want to determine this which attacker free tuples collide with which loopback free tuple, and by knowing which loopback free tuple, our end goal is of course to get a device ID, but our mid-time goal is to know which attacker free tuple collides with which loopback free tuple, and by what I explained previously with transitivity, we can deduce which loopback free tuples to collide with each other. And here's now a complicated condition to determine that, but and I'm going to what you see as basically the definitive description operator, which means a unique V attacker free tuple that satisfies that, and that can only be 1. But I'm going to explain it in, I think, a more intuitive way in the next slide here. So here we are in phase 1, and what we have here, we see a source port increment of 2 over here, and if we follow the edges here, then we see that we had a collision with this single loopback free tuple in the filling layer. And because we only send a single loopback free tuple, because we only send a single loopback free tuple, also only one of the attacker free tuples will get a source port increment. And that is this one. And by this we can deduce that both of them collide. And we will always find a attacker free tuple because in phase 1 we determined the attacker free tuples, unique attacker free tuples for all perturbation table cells. So that there will always be found a attacker free tuple. And yeah, and because only one was incremented, yeah, that means that the two collide and so forth. Yeah, then the condition looks like this. But now we have our problem with the noise again. Now noise can actually cause some havoc for us because here it can cause an increment in this value here. But what we can do is we can send this loopback free tuple in a sufficient amount of times, such that our increments caused by the noise are actually outweighted. This here one is the noise. That the increments caused by the noise are actually outweighted by our repeated sending of the same attacker free loopback free tuple, and yeah, and then the condition basically looks like this: that we have some epsilon, and this one has to be has to, for example, here be greater than 4, and we assume that our noise can or very rarely cause a increment greater than 4. So, and now we come to a case distinction, and basically this case distinction here in this algorithm, so that we just talked about the condition, and basically this case distinction is basically just to construct independent pairs over here. If we have 3 loopback tuples that collide with each other, then we can construct an independent pair from it. And we have here, let's say, this loopback free tuple is the first to collide with this with a certain perturbation table cell, which we know because it collides with a certain unique attacker free tuple. And if it's the first one to collide, then it goes over here. And this BV is basically a dictionary. The keys of this dictionary are unique attacker free tuples, and the values are the first loopback free tuples that collide with it. And I guess you can guess how this then works. We, if the first time we meet it, we just collect the first loopback free tuple that collides with this attacker free tuple. And then the second time there's a collision of a loopback free tuple with this attacker free tuple, then it already remembers this this Li from back then, and then yeah, it just constructs this independent pairs basically. So with this one, and it just if this was ordered, then it just takes the first one. It just constructs independent pairs, and it increments the collision counter because that means that there's a collision between 2 loopback free tuples over here. And then at the end, we have a termination condition. And what this condition actually means is, for time reasons, I won't have the time to explain it in detail, but if you're interested, I can explain this formula to you. But basically, what you want to test here is if your calculated device ID is so unique that the probability that a different for this attack, you kind of have a set of a population of different devices that you want to track, for example, 100 or something. And you want that the probability that another device has the same unique device ID is below a certain threshold, P star over here. And we use and in the paper they use a quite smart little trick to not such that they don't have to calculate this probability every single time. And what they use is a so-called construct a table of an A and star table, which they use to collect the minimum value of n that satisfies this condition. But I don't have the time to explain it in detail. But basically, what it does, it makes it helps you such that you don't have to calculate. Basically, node can just use this n that you increment, the number of collisions, to determine if and the number of iterations to determine if this probability here is satisfied. That the probability that the device has the same device ID is lower than a certain threshold, and if this device ID is unique enough by now, which increases with each of this n and I iterations and number of collisions. And now the interesting question is what are the countermeasures? The root cause of the attack is basically that for all network contexts, you use the same perturbation table with the same GK2 function and a predictable increment. The ideal solution would be to just have a different perturbation table for each different network context. But the problem is this is has a too high memory cost. So what we do in general, the general countermeasures that we do are now making the detection of hash collisions harder and less likely. And what we can do is we can make it more time intensive, and we can limit the time that one has to determine these hash collisions. So what was actually implemented? So the authors of this paper had worked together with the Linux kernel developers, and they implemented 3 changes. They implemented periodic rekeying. So they have rekeying every 10 seconds. And rekeying means there is a different structure of hash collisions. And by this different structure of hash collisions, there's of course a different device ID. And then, this whole algorithm doesn't work anymore, at least over time, not over space. If you're able to make this attack in less than 10 seconds, it's still possible. And what they also did, they increased the perturbation table size from 256 to 64 kilobytes. And this has mostly an effect on phase 1, because remember, in phase 1, we had to find a unique attacker-free tuple for each perturbation table cell. And if you have 256 times more table cells to fill, then that needs much more time. And a second and the last countermeasure was to introduce more noise. They changed that the increment is not by 1, but at random between 1 and 8. And by this, if, for example, 2 loopback or two free tuples collide over here, then they need a way larger epsilon. This thing with the increment. They need this increment to be. They have to make this attack go for much longer to have and choose a much larger epsilon to have a significant increment, such that they know that it was not just coincidence that maybe the noise had just by coincidence really large values every time, and their own tuples only got really small values. And and by this, hopefully the not hopefully the attack is hopefully infeasible over time. Is infeasible over time, and hopefully also over space. And and now are there questions?